stress, the maximum value of tension, which I'm defining here as S, the geometry of the structure and the crack, and so I've defined a half width of the crack as A and a half width of the panel as B. And this we define the stress intensity for that particular condition. Okay? When we look at this, what we can do is we can assess what we think to be the critical stress that's present in our structure for a specific crack length. And so the way that this is often used for design is to say, if I know what the fracture toughness of my material is, I chose my material for my design according to partially that property, then what I can do is say, well, how long can the crack be before failure will actually take place? And then what I do is I look to see, is the critical stress less or greater than the stress I expect in my structure? So that's very useful. And then the other thing that I can do is I can say, well, if I have a fracture toughness of the material, and I then use this as a failure criterion, I would say, for a stress that I know that my structure can experience, what would be the flaw length that would be associated with that particular condition? I chose the material, the service loads are things that I can control to some extent, or at least I can understand, and then I say, how large can that flaw be? Why is that important to me? Think about it from an inspection standpoint.
I think the surface finish has to be.
Well, maybe how good the surface finish has to be. I think of it more of it in terms of non-destructive inspection. I think if I can choose a component with a large fracture toughness, or for a specific loading condition of stress, the larger the fracture toughness is, the larger the crack can be before the component supposedly is going to fail. And then what that means is, the longer the crack is, the more likely I can see it and take that structure out of service before it goes critical. That's fantastic, right? We want structures in which if I walked by it and I saw a crack, that structure still, this is an airplane, wouldn't fall out of the sky, but non-destructive inspection would have an easier time to identify that flaw and take that structure out of service before something critical happens. The smaller the fracture toughness, obviously, if this is a failure criterion then for a specific stress, the smaller the crack will be, or it takes a much smaller flaw to actually result in fracture. So that's a problem. So we think that having large fracture toughnesses are valuable, but there's sort of this trade-off. And so what we like to do is we like to think that we can talk about the critical stress in our structure for a choice of fracture toughness in terms of the distribution of flaw lengths. And here is what's in your notes then to describe that behavior. So we see as the crack becomes smaller and smaller and smaller, that what happens actually is that the critical stress for fracture to take place, it's increasing. But we know that that's not necessarily boundless because no structure can withstand or resist an infinitely high stress. And so then there's another criterion that we would use to talk about, hey, how that particular structure will likely behave. So for those of you who have taken 220, you'll be introduced to Tresca before as a failure criterion, which is just really a maximum shear stress failure criterion. It assumes the material is ductile, and so what we're doing is we're comparing a critical value of stress, and in terms, this is actually the shear strength of the material, the yield strength under uniaxial tension divided by 2. And that quantity is set equal to the principal stress difference divided by 2. So this is the Tresca's failure criterion, which says that for uniaxial tension, failure will occur when the maximum normal stress, because sigma 3 is 0, this is uniaxial tension, is equal to the yield strength of the material. So any metal that has an ability to yield will yield first before it fails according to this criterion that we have associated with cracks, right? This is called the transition from linear elastic behavior to plastic behavior, yielding phenomena. So we talk about this relationship here, or mostly defined as this criterion here, as linear elastic fracture mechanics. It only applies for conditions in which the crack is larger than some transition flaw length. And so that's what we did last time, is we solved for the transition flaw length, and we said where or what is that for a structure with a particular fracture toughness and a particular yield strength. Okay? We like to look at this value because it tells us something about how flaw sensitive this material is. So smaller and smaller the transition flaw length becomes, the more flaw sensitive we say that material can be. Because of the fact that it says all flaws can contribute to fracture by linear elastic fracture mechanics. If this transition flaw length is way over here, because this material has a very low yield strength, it means that that structure is not very flaw sensitive. Structure will fail by yielding before the flaw ever really contributes to fracture. Right? Concept, strong concept, very valuable concept in terms of failures. So let's look at this criterion then in terms of how we can use it. So this is the LEFM criterion, the linear elastic. So this is an elastic phenomena, fracture mechanic criterion. It says that fracture occurs when the mode 1 stress intensity is equal to the fracture toughness of the material. The point of this course is failure analysis. So I want to think about how I can use this particular criteria. Let's say that I have a structure, I can see the fracture surface, and I can actually measure what the flaw length is. Okay? So I can determine the transition between stable fracture, a fatigue crack, let's say, and then unstable bolt fracture. So I have this value. And from that flaw geometry, I can get the value of F, the geometry factor. What can I do with this thing? What can I do with that knowledge, that information, that data? If I know the fracture toughness of the material, I can do what? I can estimate what the stress was, the maximum stress in that structure. So I can see, hey, was that load or that stress within the bounds of what we expected to have happen in that structure? So I can see if it was overload. Okay? That assumes, again, that this flaw length was greater than the transition flaw length of the material. If it wasn't, then I would say, hey, this shouldn't be a fracture problem. Now, what happens if I have that crack length, okay, and I actually also know, I expect to know what the stresses were on that structure at the point in which failure took place. So I have the geometry factor because I know the flaw length, and I know the stress. What can I calculate? Calculate what apparent fracture toughness that structure is in, right? And what happens if I find out that it's different than what's reported for that material? I made a mistake. Shoot. Go back, I check my numbers. Stress again, flaw length again, calculations, and I think I find again a value of K1C that's lower than what I expected. Say either the material is different, do I go back and I check the chemistry of the material, or what I do is I go back and I find out what environmental conditions could have caused that fracture toughness to change. Could it have decreased? Can we have fracture toughnesses that change? They could, right? So I start looking at conditions that do exactly that. And then the other thing I do is, let's say, for example, I don't have the flaw length because the contact characteristics obscure the crack and the transition between fatigue and non-fatigue. I know what the stress is, and I know what the fracture toughness should be, right? I can go back and I can check what the flaw length is, and then for that flaw length, I go back and I try to check to see again if I can understand what the fracture toughness is. So there's many things I can do here as a failure analysis expert. Okay? But I want to make sure always that I check this. Was that flaw greater than the transition flaw length? Because if it's not, I should have seen that that structure failed by yielding and not by fracture. Okay? So there's a thing that can influence that behavior, and that is something that's called the limitations of linear elastic fracture mechanics. If we happen to look at a structure, and so this is a 2D structure, representation of a structure with a crack, and if I look at the boundary of that crack, the surface of this body is always under plane stress because it's a free surface. It requires that this is a plane stress surface. There's no stress vectors pointing out of that free surface unless I push equally and opposite. And so what happens is we find out that the plastic zone, the zone of plastic deformation in front of the crack tip actually changes from the surface to the interior of the body. And so this figure 6.5 out of Stephan's textbook shows exactly that. it shows you that the zone of plastic deformation, what's called the plastic zone size, is always larger on the surface than it is in the interior. And the point of this, or the importance, is the fact that if you have bodies that are thick enough, the interior is under what's called plane strain. And that plane strain condition is really this. If, in this case, we say that the strain in the z direction, the through thickness, is limited, this is plane strain, then, the epsilon z, the strain in the z direction, can be defined by generalized Hooke's law. There's generalized Hooke's law for the outer plane strain defined in terms of the other components of stress which are present in that particular structure. So that says in this case we can solve for sigma z, and we find that sigma z is equal to nearly the average of sigma y and sigma x, if we think about this component just undergoing the onset of yielding, where Poisson's ratio will tend toward 0.5. So it says that sigma z is an intermediate stress. It's almost the average between sigma y and sigma x. Yeah, right? So what does this mean to us? It means that if we have very thin structures, then we don't have enough thickness on the interior for a plane strain condition to develop. And then what we find is yielding plays a much larger role on the behavior of that structure. And what will happen is that the material will act like it has a much larger resistance to fracture because yielding tends to occur near the crack tip. And that starts to ovalize the crack tip, and it changes its actual geometry. It reduces the stress intensity to the stress concentration. As the structure becomes thicker and thicker, then what happens is it tends towards plane strain. That means that the strain in the z direction will approximate towards 0. The stress in the z direction will become an intermediate value, and that will confine the plastic deformation in front of the crack tip. So then what will happen is that fracture will be more likely to take place because, again, this is a linear elastic fracture mechanics process. And since the plastic zone size has been decreased, then that means that this becomes confined to a more elastic process. So you need to be aware of the fact that whether your structure is thick or thin, and you can have situations where someone actually increased the thickness of the structure to reduce the stress, but they made that structure be more likely to fail by fracture because it started to tend towards a plane strain condition of near crack stress. Okay. Or, so when we see reported values for fracture toughness, they're always defined according to ASTM E399, which says exactly that we need to always measure the fracture toughness according to a plane strain condition, because that will be the lowest resistance to fracture that exists in that structure. So that all bodies that have geometry which are larger, plastic zone size, smaller in thickness, they'll be safe. They'll have that added safety, that plasticity will make them safer. So there's a lot of science in this process. And this is exhibited then by just looking at fracture surfaces. So let's say, for example, these are ASTM geometry specimens. They're what's called a compact tension specimen geometry. For those of you that haven't seen them, they look like, maybe I'll bring one to class. They look like this. They're just a body that has a specific shape defined by the ASTM standard. They're used to be able to initiate a crack and then to be able to grow that crack and evaluate fracture toughness. So you're looking at a portion of that, and then what you want to look at is this part right here. So this is a thin, an intermediate, and a thick body structure. This is the Z direction, and you can see that this went from a slant fracture to a small amount of shear lip to almost no shear lip at all. What does that tell you? Slant fractures or shear lips indicate ductility, and so lower amounts of shear lips means less ductility, and no shear lips means almost no ductility. And this is the same material. This is just a change in the stress state, right? So this is looking at an in view of this, showing you single and double slant fractures can occur, but they both say the same thing. They say ductility. Thicker body starts to have smaller shear lips, And then a very thick body, that certainly transitioned to plain string, has very, very small portions of those shear limits. So that's an important observation for you when you look at those fracture surfaces, right? It just says, hey, this has less ductility, and the reason is because of this plain string condition. So when you look at structures and you look at the way that they evaluate fracture toughness for them, there's some conditions on crack length and thickness of the body that are required to make sure that you evaluate the resistance to fracture in the plane strain conditions. And this is it, that if you know the fracture toughness, apparent fracture toughness for that material, and you know the yield strength, then you must have a crack length that's greater than this estimate, and a thickness of the body, that means in the Z direction, that's greater than that quantity as well. And this is just a description of the apparent fracture toughness for an H11 steel. This is a high-strength steel with an ultimate tensile strength that's on the order of like 1,500 gigapascals. That's huge. That is really amazing. So when you see this and you look at thickness, look at what happens to the fracture toughness as a function of thickness. This material becomes decreasingly resistant to cracks as that body, the thickness increases. And then we define the fracture toughness as the floor of that, the plateau. So the point is here that you need to think about the thickness of the bodies when you're looking at them from a forensic perspective, because that could be simply the transition from a plane stress to an intermediate to a plane strain condition. Yes.
Up in the corner there, pop in.
Pop in means that the crack popped in. That means that the crack popped in without any no additional deformation around the crack tip. So pop in would mean that it's a dynamic snap in of it. And so in this case, these black dots represent the fact that the material was brittle enough that when enough opening load was applied, the crack popped in, it initiated dynamically in order to be able to continue. Whereas in this case, what we're doing is we're trying to start a crack by placing a notch and then sawing the notch with diamond paste and getting it to be very sharp. But then still what will happen is that crack will start to ovalize, and for very thin bodies, it'll start to develop plastic deformation. So the crack development is not necessarily one of those dynamic.
So no pop in is going to be more like it tears apart versus it just pops apart? Or is it?
No, this is about the crack initiation. The initiation of the crack and sort of the developing from a notch that's sawn in order to be able to have the shape. And then its progression is something that's still maintained or required to be a very brittle The pop-in event is a transition from a sawed-in notch and the apparent crack that we can develop by experimental protocols, and that which is really true of infinitesimally sharp crack with no release of curvature. All right, so the other thing that can happen that can change this quantity that's important in this linear elastic fracture mechanics definition is just temperature. You know that all of the body center cubic materials that you've been looking at that you saw undergo transition temperatures can exhibit changes in fracture toughness between the upper shelf temperature regime and the lower shelf temperature regime. So you want to look to see which temperature is important in that particular fracture for the material. So you can find that just inappropriate choice of the material and its DBT point in comparison to the environmental temperature can be the real root cause. Fracture is just what happened, but the cause is because it was the temperature and the material was chosen inappropriately for that particular environment. Now, another thing that can happen is you can find that there's a mutual competition between strength and toughness. Okay, the mutual competition is when one goes up, the other one usually goes down. And so this is a good plot of fracture toughness for a 4340 steel. So this isn't chromoly, this is nickel, chromium, molybdenum, is a function of a heat treatment process in which was used probably to change the yield strength of the material. You can see what happens is as the material was heat treated, quenched and then slightly tempered to be able to get large yield strengths, the fracture toughness decreased significantly. And you can also see what happens then to this transition flaw length here, as a function of the increases in yield strength that come from heat treatment. If I heat treat for strength, thinking that that's the major mode of failure, and I forget about fracture toughness, what did I do with the transition flaw? It drops substantially. And then what does that mean, that structure, how will it behave? Looks the same, but it will be much more sensitive to flaws, and much more likely that flaws will dominate its behavior rather than yielding. So yielding can be lost, or a yielding phenomenon in terms of material can be lost. So be careful. Be aware of heat treatments that were used, but not necessarily done appropriately, or they were used by someone who thought that it was smart to increase the yield strength more and temper back a little less than really was probably appropriate for resisting fracture. Okay? Great. So, now, we start talking about flaws in terms of when they're going to contribute to fracture. So let's say, for example, that we have a flaw within a structure and it's not quite critical. It sits there. Can we forget it? It means the structure is going to fail by yielding for us. We don't want to forget it because what can happen is it can grow. So we want to know how long will it take, or was that fatigue crack growth process really something that could contribute? So I've got another, let's say, this is like a quiz. This is a case study. So this is polycarbonate. All right. So this is a polycarbonate tensile specimen. It has not been subjected to any loading, and this is one of the specimens that actually was subjected to the point of failure. And I'm going to pass these out, and then we're going to talk about whether this was ductile or brittle. Okay. So that's that, and I'll give you the loop in case you want to see it, because actually what you can see is you can see radial lines on the fracture surface that are representative of the direction of crack growth from the point of initiation. All right, so we can have flaws that were present in our structure from a lot of different sources. They can be intrinsic material defects, so they can be inclusions, they can be voids, etc. They can be surface flaws that result from either manufacturing or service. Or what can happen is as a result of relatively large overloads that cause plastic deformation. We can get the development of what's called extrusions or intrusions. So at the surface, we can get the development of some well-defined intrusions that develop because of the slip planes that activate near the surface. And that will cause a stress concentration that's localized and eventually lead to potentially stress intensity. And then what we can also get is we can get persistent slip bands that develop near the boundary of the surface along very well-defined slip band orientations of that material, which is going to be a function of the alloy content, but also in any of obstacles that prevent the distribution of those particular slip bands. If they're localized, what can happen is they can develop small cracks that then transition into a very well-defined crack that grows under mode 1 loading or tension. So many sources. So what we want to do is we want to say, hey, we might have flaws in structures, and then what we want to do with that is we want to say that we know that they can grow if they're subjected to an adequate driving force or an adequate magnitude of stress under their service loading condition. And then what we want to do as well is we want to say that we can predict what that rate of cyclic loading will be from experiments that are conducted with that material in which we control the particular conditions. But we want to make sure that we're using equivalent magnitudes of the amount of the driving force or the amount of the stress intensity that actually was contributing to fracture of that particular material and surface. And then eventually that crack will grow in a cyclic manner until it reaches the critical value that we can apply linear elastic fracture mechanics. Right? So this is a process in which we assume all structures have flaws. We want to know then the conditions under which those flaws will grow cyclically, and then we want to know how fast they'll grow to predict how long it'll take before that crack gets to a length that satisfies linear elastic fracture mechanics. So in order to do that, we're going to follow some guidance in terms of estimating fatigue crack growth rates. And the most well-known standard is ASTM E647, which is defined as the test method for measurement of fatigue crack growth rates. So here's a good good example, you can see from this cross-section, this is exactly that specimen that I showed you right here. That is that compact tension specimen geometry. It's used both for evaluating fracture toughness as well as looking at fatigue crack growth rates. And then what's done is we monitor the incremental rate of cyclic crack extension that develops in that particular material as a result of the conditions of loading.
What are those like very light striations running along the crack?
So in this case, you're looking at these things which are present right here. That dates that specimen to about the 1970s, 1980s. So that's actually the period of time before digital cameras were really used. So the way that this process was actually conducted is we used a crack gauge on the interior of the specimen, which told us the opening displacement as a function of loading. And then what we also do is we used a grid in front of the crack tip in order to be able to count the number of lines, which told us the physical distance over which that crack grew for a certain number of increments of cyclic loading. So this is although this is a fantastic textbook, we're just not always updating the figures and showing the latest and greatest. So that's exactly what that is. And then what we're going to do is we're going to conduct cyclic loading to be able to monitor that incremental crack growth as a function of the cyclic loading that was applied. So we will plot something that looks probably just like this. We'll have our specimens that we'll decide we're going to subject them to a cyclic load with a range of that cyclic load of a certain magnitude. And then what we'll do is we'll plot the crack length from an initiation point through the point where it goes unstable on a graph that looks just like this. Okay? And from that then, what we can do is we can actually take the distance between the data points, defining a delta A, and the number of cycles over which this test was conducted to get a delta N, and look at exactly that, the incremental, so that means the amount that the crack grew in one loading increment. And that defines to us, as long as those data points are close enough, an incremental crack growth rate. Okay? If the data points are too far away from one another, of course, that's not a very good representation of the discrete differentials. But as long as the monitoring is done appropriately, then we have a way to be able to get an incremental crack growth rate. And the driving force, the things that were involved in making that crack grow, is really something that we can define for a crack, which is the stress intensity. Because the load is undergoing a range from a minimum to a maximum, then we can define the stress intensity as undergoing a range from the minimum to the maximum stress. Okay, so we're defining a stress intensity range by the maximum and minimum stress for that particular structure. Very straightforward. And then what we can do is, with all of this data, we can get or define dA dN as a function of delta K, and delta K comes from simply the value of the geometry factor, the knowledge of that stress range that comes from the loading range, and our knowledge of that incremental crack length over that history. Right? And we plot something like this, which is called the fatigue crack growth diagram. Here plotting dA dN is a function of delta K for, in this case, a large number of specimens. So each one of these data points represent a result of an increment of crack growth over a certain span of cyclic loading. So what's plotted is the average stress intensity range for that incremental growth, and then of course the average or the delta A, delta N that was obtained for that incremental crack extension. We usually see a sigmoidal distribution that looks just like this. So the majority of materials that you'll see, if they happen to be a metal, a plastic, they'll exhibit this kind of behavior. And we then have a way to be able to characterize the responses. We look at one thing which is called region 1, which is called the initiation regime also. And this defines a condition in which we're near the point where the crack is starting to initiate its cyclic extension. You know, we have to get a minimum value of delta K in order for that crack to start to grow. If we have delta K that's less than that, the crack can be there, but it doesn't care that the cyclic loading is going on. It just stays dormant. So delta K threshold is a threshold stress intensity range that actually must be achieved for that crack to undergo cyclic loading. We like to see that as a large value for our structural materials, because the larger the delta K threshold, the more resistant that structure is to cyclic crack growth. And then after that, that means after the region 1 response, we talk about the rest of this with regards to some other regions. So here's region 1, here's the intermediate region, which we define as region 2, which I'll talk about, and then region 3, which is called the region of instability, or the tertiary regime, which starts to help us understand, you know, the fracture toughness or characteristics of this material. The majority of fatigue crack growth life for this structure actually is accumulated here. It's where all of the incremental growth actually took place. And so we like to plot this data on a log diagram, because what we see is that data in this regime follows a linear trend line. And we can apply then a power law defined as the Paris law to that specific relationship, where if I take the log base 10 of both sides of that expression, I get the definition of a straight line, right? I get log dA dN equals log A plus n log delta K, where n is just the slope of that data on a log diagram. So that's a fantastic relationship, okay? And we then try to characterize the fatigue crack growth responses by then these three quantities. One, the threshold, stress intensity range, as well as the C, the coefficient, and the M, or in this case, if it's defined using A and N, the A and the N values that you'll see for those materials, all right? You can find A and N, the coefficient and the exponent, for nearly every engineering material you ever want to know in handbooks, because it's been developed by people that are always worried about cracks growing cyclically in structures. Right? So let's say, for example, I want to be able to evaluate the cyclic crack growth within my specimens. I can use what's called the compact tension specimen that's right here. But not all of the materials that I have available to me will allow me to make that kind of specimen. I might want to conduct tests using other kinds of specimen configurations. Schematics are shown there, and some other kinds of specimen types that are used to looking at fatigue crack growth are listed here. And what we do is, if we look at the dA/dN response as a function of delta K, as long as we quantify the responses that way, we find that the data follows exactly the same trend. Exactly the same trend, okay? What's the importance of that to you? So why do I even mention that? It seems like just testing. This is just a geeky comment from someone that likes experiments. Is it neat? So in this case, right, each one of these specimens has a different geometry factor that's used to be able to describe the stress intensity, or the stress intensity range as a function of delta S. But what it tells you then is if we get the same kind of crack growth in a cyclic manner for all these different specimen configurations, then as long as we just define the stress intensity accurately, the same consistency will occur in our structures that are present in service, as long as we can define the same things correctly. The magnitude of the stress, the global stress, the nominal stress, the geometry factor, and the crack length at that position. So geometry of the structure makes no difference. Only that we know the stress, we know how to calculate the geometry factor, and we can accurately look and see or estimate what that crack is. All right? Fantastic. So this is, you know, maybe not that impressive, but really it is the door that opens up that says you can apply this to all of your materials. Okay? So let's think about applying this to materials, but also think about its application to failure analysis. So again, here is this fatigue crack growth diagram that describes the entire range of fatigue crack growth response for this material within region 1, region 2, and region 3. We can see a well-defined region 2 response. The Paris law has been applied. And then what we know is we know that that stress intensity range is just basically a function of the loading range that's present on that particular structure, and then the rest is all geometry factors, okay? That's all that's going on, that's all geometry. So first, I want to make sure you see, when you look at a diagram like this, that you're kind of prepared to think about what it means. okay, physically what it means. First of all, what you want to think about is that this represents the growth rate, and this represents a function that's primarily changing is the crack length. These quantities, the specimen thickness, the specimen width, etc., those are constants. Those are geometric constants. So the only thing that's changing in this relationship, this delta K relationship, is the crack length. So this says that the stress intensity increases as the crack length in the structure increases. So this is a result of, as the crack gets longer, it actually causes an acceleration of the speed or the rate in which the crack grows because the stress intensity is getting bigger. There's more driving force, not because of the surface conditions, it's happening because the crack is increasing, which increases the magnitude of stress intensity. And I'll point out why that's important in a little bit. So then the other thing that you want to look at is you want to look at slopes. Slopes say something very important about this response. Let's say that I have a slope that's very high. What does that tell you? It's almost vertical. And then let's compare it to a slope that's almost like this, almost horizontal. This is the easy one to think about physically. If the slope is horizontal, it says that regardless of the fact that the stress intensity is increasing, function of the increasing crack length, the material doesn't care. Oh, that's a beautiful response of the material. I'd love to have that material for my structure. Versus one that goes like this. If I have a material like this and the crack starts increasing a little bit in length and then it just takes off like it's in a race, that's not a good material for me, for resistance to cycle crack growth. So N, that slope quantifies the material sensitivity to the stress intensity range. And then A, which A is just going to be an intercept where the stress intensity range is equal to 1 because the log-log relationship, you can't see it, it's down here up on the far left. It really represents something which is the effective growth rate. So you can think of C being the height. The larger the C value, the larger this distribution shifts to the right, or shifts upward. So if I compare two different curves and I look at their positions on this diagram, the best materials are down here. Low slopes and low growth rates despite the fact that they have large stress intensity ranges. And if I'm up here, it means that the material is not quite as good because it has fast growth rates for low stress intensity ranges, okay? So you always want to think about that when you look at materials from a design perspective, but you also want to think about when you look at materials comparing them for what happens by the environment. Questions about that? This can be, you were introduced to this in MSc 362, correct? Okay, and you feel strong about this? Good, great. So now we're going to apply this to failure analysis. So we can estimate the inherent life in our structures just by simply taking that relationship with Paris law, rewriting it in terms of the Dn quantities, in terms of the stress intensity range, and then integrating from 0 to the final number of cycles, which we define to be a apparent limit for that particular structure. This only is valid for a condition in which f is equal to a constant, and then n, the value of our exponent here in the Paris law, is not equal to 2. But we can estimate then the number of cycles of failure between a sub I, the initial flaw length, and the final flaw length. The final flaw length is just obtained from this, of course. So if we say now we have a structure in which failure or fracture will take place according to linear elastic fracture mechanics, the fracture will take place when this is true. So when we have a fatigue cycle, we want to know what the maximum stress is in that fatigue cycle, and then we know that fracture will take place when that crack reaches a critical length, right? Length that enables fracture, or F for failure, all right? So which is listed right here. So this is simply saying that I know that that critical flaw length is going to be equal to this that I can estimate this A sub C, which is equal to my final crack length at fracture. So if I know my initial flaw length, I know what my final, most likely flaw length will be at fracture, I can estimate an apparent life. And then I can, with that, decide, hey, I only want to use 2/3 of that, take that structure out of the service before that.
So what is NDE?
NDE. So A sub I is either specified from something that you know or non-destructive inspection or non-destructive evaluation. It might be the minimum flaw length that you can see from non-destructive evaluations. Okay? So a great way to estimate what we think we can get for lives of structures. And so now we have values that I just present to you so you can see some representative values for ferritic pearlitic steels, some martensitic steels, of course, austenitic, non-ferrous materials. Values of N that you'll see for most rock form metals ranges between about 2 and maybe 4.5 and 5. But you'll see something very important about what we said about N. So if I look, I have one material here, this is this A356 T6 cast aluminum. You can see that its slope says that the Paris law exponent is 11.2. What does it tell you about that material? Very sensitive to cyclic crack growth in comparison to those rock form metals. Definitely true, and we find that in general, cast materials, aluminum alloys, magnesium alloys, are generally relatively brittle. So indeed, this is actually a contributor to something that we see, and then their response is one in which those cracks are much more sensitive to cyclic loading and driving forces. So be aware of that. Okay, so what can happen in our structures? One of the things that can happen is that we could have changes in conditions of materials that result from environment. So we could have heat treatments or heat affected zones which might change the local fatigue threshold of the material. So I go back and I remind you what we see in these fatigue crack growth diagrams is this stress intensity threshold. It's something that's very specific to the material and its microstructure, because it's all based on the obstacles to preventing that crack from being able to grow. Anything that changes those obstacles, their size, their effectiveness, can take away that stress intensity threshold. So one of the things is overaging. Overaging, which is very, very common in aluminum alloys, can reduce that delta K threshold and enable then fatigue crack growth to initiate from existing flaws. So this is what's, these are two different near threshold regions of fatigue crack growth response. You've seen a cross section for aluminum, copper, lithium alloy, which has been tested without overaging. Okay, that means in the T3 temper, and then after overaging, and you see what happens. And then in this case, this material has no microstructural obstacles that are actually preventing that crack from growing straight. It just simply grows according to the direction of the maximal opening mode stress. Simply a result of overaging and minimizing those precipitation hardened zones to be the appropriate size according to knowledge of the lunar process zones that we want to achieve. The other thing that can happen is we can have a change in temperature. So if we have a ductile to brittle transition temperature for material and that temperature decreased in the environment, we can lose the near threshold regime response, and our delta K threshold means nothing then anymore for that material. So we can have things that also occur in the Paris regime and also the fracture toughness in fatigue, but really threshold effects are most commonly changed by this problem with heat treatment and or changes in temperature or mixtures. Okay? I had when I was a graduate student, well, I felt good. I had a Cannondale bicycle. It was one of the first mountain bikes that were all aluminum frame plus aluminum forks. And about 6 months after I got it, it was recalled. And the reason is because there were a lot of forks that had welds on them that actually underwent this exact same problem, that they were subjected to a temperature that changed the threshold characteristics of the material. And many of the riders, which were going off-road, had their front forks actually fracture, fail, when they were undergoing some more aggressive type riding, because the cracks were long enough that the material was subjected to fatigue crack growth. So this is a very, very common problem. I show you examples now of fatigue crack growth data for steels. In this case, this on the left is a good example of ferritic steels. So we're looking at most of your plain carbon, high strength low alloy steel responses here, and you see the straight line on the log-log responses. Tells you that the Paris regime applies very well to this material. Same kind of thing, the bounds now defining responses for the martensitic steels. This doesn't mean martensite, this means the martensitic versions of steels, for example, the stainless steels that are common in this martensitic condition, 400 series, etc. Tough materials, but still undergo fatigue crack growth and follow the Paris law responses. Okay? We would use those for design or for checking something that will become evident in the fit. Here's a comparison of all the steels together, just showing you the bounds between the austenitic, the ferritic, and the martensitic steels, and the range of the bands that accommodate all those materials. Right? We're doing this because we want to actually use it for a fracture or failure analysis. And so what we want to do is think about the characteristics that that cyclic crack growth process will represent in the materials. Most cracks that start from the surface, if they don't start from cracks that are initiated by manufacturing, they'll start from slip bands, and these will extend over about 2 grain distances, maybe about 20 to 50 micrometers in distance, and then they'll transition to a mode 1 growth. That means growing perpendicular to the maximum opening mode direction, and then it continues to extend in that way. Okay? Most times we'll have cracks in structures, so we never see that. We can't see the initiation point by that transition, but that's a very common mechanism. But when we see fracture surfaces, what we look for is we look for striations. And so this is the most common characteristic of fatigue crack growth. These striations are a result of the incremental extension of the crack with each loading cycle. And they are then a trace of the path that the crack followed until it gets to a point of instability or ultimate fracture. And then what we see is the onset. At this very high magnification, you're looking at a singular void because of ductility in this material that took place. So we always look for fatigue striations in thinking that fatigue crack growth might be a contributor.
So if you're running a fatigue test that has 200,000 cycles, are there going to be 200,000 striations?
They might not all be evident, and most likely, I don't know that anybody's ever counted that far because we have to do that in SCM. So there's probably better things to do.
But normally there should be one for every load.
There'll be one for every load. So we'll talk about this more